Hey there, chemistry. I want to take a minute and recap the Bohr model now that we've done a little bit of work with it. I just want to make sure that we take the time to summarize a couple of the really important parts that come out of this molecule. So I have a Bohr model of the atom in front of me, and you can see around here is the nucleus. That's what this red dot in the center is supposed to be. That's supposed to be the nucleus. We can give that an N. Or better yet, since Bohr built his model off of the hydrogen atom, we should just give this a +1 because they're in the hydrogen model, the nucleus has a +1. Fun fact before we go any farther, if you ever see a Z, Z indicates the charge of the nucleus, which is also equal to the number of protons. And so in this case, Z for us is equal to a +1 because we're dealing with hydrogen here. Hydrogen has 1 proton, so it has a nucleus of +1. So nuclear charge as we go forward is going to become more important to us. And already we've seen a couple diagrams that throw Z's onto them. So I just wanted to take a minute and show you what those are. Another symbol you might see on Bohr models is the N. The first ring is going to have an N equals 1. The second ring is going to have an N equals 2. The third ring is going to have an N equals 3. In this drawing, we would have all the way up to N equals 4. So N is typically talking for Bohr, he called N's orbitals. Nope, he called them orbits. Bohr called each of those rings orbits. It's basically the allowable distance where the electron can live. It's basically the space where the electron can live. So Bohr called that space orbits. We're going to see what those orbits become in the quantum mechanical model when we go ahead and we talk through our current model of the atom. You may be more familiar with them being referred to as energy levels. And that's certainly appropriate for this model to call them energy levels, because in this model, what we really want to come out of this is the movement of electrons. And electrons are going to move by either gaining energy. They either absorb energy or they release energy. And so it's a pretty appropriate thing to call these rings energy levels because as electrons gain energy, they move levels. Okay, so in the model that we saw in your packet, especially in number 19, you really had to deal with Bohr's model in number 19 and deal with these transitions of the electron in Bohr's model. And hopefully what that drew the distinction between was the parallel between Bohr's model and the hydrogen line spectrum above. Because the line spectrum is what Bohr used to make the model. So again, when we look at this, the electron is going to be transitioning around this atom. So for hydrogen only has 1 electron. It has 1 proton. And therefore, to be neutral, when hydrogen is neutral, it's also going to have 1 electron. So I'm going to just draw a blue circle here for the electron. Okay, now, when this electron gains energy, it moves. So I'm going to draw a little lightning bolt-ish arrow that points at the electron, and that's going to indicate an energy input. Now this energy input, when the electron absorbs energy, can be a lot of different things. You could take metal or a salt and just put it in a fire. The fire is going to provide ample energy, and the electrons in these atoms that you put into the fire are going to absorb the energy from that fire. It could also be electricity. Okay, we can do something similar to a cathode ray tube, where we take a gas and we electrify it by running electricity through it. We have kind of a version of this called a Geissler tube, and a Geissler tube literally takes a tube full of gas, and electricity is run through the tube, and whatever gas the tube is filled with, the electrons of that gas will absorb the energy, and they will start to move. So the source of energy can be a lot of different things, but anyway, the electron's going to absorb energy, and when the electron absorbs energy, it moves. It moves to a higher energy level. So this is kind of one of the key points you need to take away from the Bohr model, is that when the electron absorbs energy, the electron is going to jump away from the nucleus. I ran out of room there. Okay, when the electron absorbs energy, the electron is actually going to move away from the nucleus. And so the electron is no longer in our first energy level. Now the electron can be found in the second energy level. Okay, now when the electron is as close to the nucleus as it can be, that's called the ground state. Okay, the ground state is where the electron is as close to the nucleus as possible. Okay, so our electron now is not as close to the nucleus as it possibly can be. So we would call this electron, we would say this electron is in an excited state. Okay, so an excited state has more energy than a ground state. So I'm going to say higher energy, and you can think of this as a stack of books, right? As you stack the books higher and higher and higher, you have physically put energy into the books. And now those books contain a lot of potential energy. If the books fall off the shelf, they can do some work because you have physically used height to store energy in the books. And this is kind of what happens to the electron too. The electron has absorbed energy and as a result moved farther away from the nucleus. And now that electron has stored energy, it has a lot of potential energy. That storing all that potential energy also makes for an unstable system. So now the system is unstable. The electron isn't going to stay there. The electron eventually is going to give off that same amount of energy that it took in. These really should be the same color because it's the same amount of energy. I'm going to change that color. Okay, so now that electron is going to give off the same amount of energy that it took in. And in the case of hydrogen, the hydrogen model that we looked at, it was giving that energy off as light. We'll talk about that in just a second too, but stay with me here. When the electron gives off that energy, sometimes as light, then the electron is going to fall back down to its original ground state. Okay, so again, our takeaway here is when the electron releases energy, it's going to fall closer or fall towards the nucleus. Okay, so this is a good summary of the motion of the electron. As the electron absorbs energy, it moves farther away from the nucleus. As the electron releases that energy, it's going to fall back down closer to the nucleus. That's a really good summary of the electron's movement. I do have a couple points here to make to show you. So I'm going to erase what's on the board and kind of move on here. Okay, so notice in your Bohr model that the electron in that Bohr model, it started in the second energy level. I'm going to label these again. 1, 2, 3, 4. And it really only transitioned between the energy levels 3, 4, and 5, I believe, and 6, and the second energy level. The second energy level always seemed to be kind of the home base for this electron. And that's because these transitions between 2 and 6, those give off the amount of energy that the electron absorbs, it also gives off. And so when it gives off this energy, that equates to moving between the second orbit and the sixth orbit, the energy that it gives off is visible light. Okay, and you may be thinking here, hold on, Martins, I thought you said the first energy level was the ground state for a hydrogen atom. It is. That's true. However, when you're transitioning between the first energy level and any of these other energy levels, so 1, 2, whatever, you're going to, I guess we should keep our variables consistent here. Whenever you're transitioning between energy level 1 and the other energy levels, what you're going to get is invisible light. Now, that's kind of a deceptive term. Basically, what I'm talking about is you're going to get some other wavelength of electromagnetic radiation. And that's what the extension questions were getting to. Oh no, not the extension questions. Oh yes, the extension questions. Extension question 24 is asking you to propose a transition that involves light that is ultraviolet. And then B is asking you to propose a transition that would result in the emission of infrared light. And so these are those other types of light. Infrared, ultraviolet, and then you can go the whole gamut of the electromagnetic radiation if you have the right transitions. And so this is why our model always used the second energy level kind of as a home base, because it resulted into visible light being emitted, and that's really the easiest one for us to talk about. But the electron has a ground state in the first energy level, and the electron can transition from the first energy level also. That just results in infrared and ultraviolet light. Okay, now that's the other thing I want to talk about is just kind of wrapping your brain again around this relationship between light and energy and distance. So remember, Bohr built this model off of the hydrogen line spectrum, and each of these colors that you see, like on model 2, each of these colors is going to correspond to a specific wavelength. So you can see that red is specifically 656. It's not 655. It's not 657. That color corresponds with a very specific wavelength. Okay, and we've already seen you using the speed of light equation that if we have a specific wavelength, we also have a very specific frequency. Well, there's this other equation that we referenced before that gives us a relationship between frequency and energy. And so this is really the packet of energy. If the electron is going to move from the first energy level to the second energy level, it has to absorb a very specific amount of energy, or a packet of energy, so to speak. Well, this is the energy that it has to absorb. And when that would be the energy it has to absorb. And when the electron emits that energy and falls back down, it's going to emit the exact same energy. So if it emits an energy of with 656 wavelength like hydrogen does, we can use that wavelength to calculate to the energy that the electron is giving off, and therefore the energy that the electron also absorbed. So there's this very specific relationship here. Specific color means a specific wavelength, means a specific frequency, means a specific quantity of energy. And that's what Bohr built. Bohr really just built the very last connection here, where he equated a very specific amount of energy with a very specific distance. Notice that the first energy level to the nucleus is always a very specific distance away, a very consistent distance away. Also, notice that the energy levels, like the energy level between 1 and 2, the first energy level and the second energy level, that is a very specific distance. And that distance is actually different than the distance between energy level 2 and 3. And that distance is different between the distance between energy level 3 and 4. And if you look at the model, okay, that distance between them just keeps shrinking and shrinking and shrinking, right? So very specific distances that Bohr built into his model to correspond with these very specific energy levels. Okay, last pattern that I really want you to see, that I want to just state out loud so that we're all on the same page, is the transitions, or those distances, and the wavelength. So you might see that as you filled this out with question 19 and question 20, you should have noted a transition, a color, and a wavelength. And what you notice as you do this is A has the largest transition, so a large distance, also known as transition, has the biggest transition. I believe it goes between 6 and 2. Okay, so a very large distance traveled leads to violet. And violet for hydrogen is 410. It's a wavelength of 410, which is the smallest wavelength that hydrogen emits in that visible spectrum. Violet is 410, red is 656. So a very large distance provides for a very small wavelength. But remember, as wavelength goes down, what happens to frequency? Remember, they are indirectly related. So as wavelength goes down, frequency goes up. And so violet is going to have the largest frequency. It's also going to have the largest, notice here, frequency and energy are directly related. So as frequency goes up, energy also goes up. So it's going to have the largest frequency. It's also going to have the largest quantity of energy absorbed and emitted. So a very large distance means a very large amount of energy. Small wavelength, yes, but that's only because they're indirectly related. Very large frequency, very large energy. Okay, so that's a lot of information. It's pretty equation based, it's pretty theoretical stuff. This would be worth spending some time drawing pictures, relating your equations to the pictures, maybe going through and explaining this relationship between color, wavelength, frequency, energy, and distance to someone. The more you work with this, the more you manipulate this, the more you're going to understand it. We are going to take another day. We spent a little bit of time working with these concepts in the POGL. We're going to take another day and work with these concepts in a lab. And so hopefully that will give you another opportunity to kind of see it and work with it and draw some connections. But again, you got to do that work too. You got to read your own level of understanding and understand where you stand. And if you need more practice, going to get that practice. That is the sign of a good student. So take a moment, reflect on what you know, and get the practice you need. One of the things I want to do just to end this lesson, because it has been so abstract, is to show you something very practical that all of this understanding does for us. So in order to look at that, I want to look at a couple examples of a line spectrum. So here I have three different things. I have a continuous spectrum, an emission spectrum, and an absorption spectrum. So notice the continuous spectrum is like light that is given off from a white light source. The sun is a white light source. And notice white light actually contains every single wavelength. There is not one wavelength that is missing here. Every single wavelength is shown. 656 nanometers is here, 657, 658, 659, all of them. They're all here. That's why it's called continuous, because there's no break in the wavelength. So the sun would be a good example of this. White light would also be a good example of this. The sun is white light, but a white light bulb would do the same thing. Okay, now down here you see an emission spectrum. So this is what we've been dealing with. We've been dealing with light that gets emitted by a specific material like hydrogen. So when hydrogen absorbs energy, that energy is absorbed by the electrons of hydrogen, and the electrons of hydrogen are going to move up and down, right? And then as they move up and absorb these energies, they're also going to fall down and emit the energy as light or as electromagnetic radiation. And then we're going to see the exact wavelengths that get emitted because of the distances between the energy levels. So that would be an emission spectrum. Now, an absorption spectrum also exists. You may hear this one referenced. It's actually just the inverse. It's not the light emitted by a source. It's actually the light absorbed. So if you throw sunlight at a hydrogen atom, it is going to emit this very specific wavelength. It's going to absorb all these other ones. And so emission spectrum and absorption spectrum for a specific material are just going to be perfect opposites. Whatever the emission spectrum emits, the absorption spectrum absorbs, and vice versa. So that's the difference between them. Our line spectrum is the emission spectrum. So that's going to be the one that we're going to work with the most this year. Okay, now with that in mind, here is an example of some emission spectrums for a couple elements. We have aluminum, we have copper, we have lithium, and then we have some unknown mixture of the three above. Now There may be other elements in this unknown mixture, but we're just going to look at these three. So this is a very practical thing you can do with line spectrums and this whole concept of the model and the orbitals. If you can collect light coming from a star, then we can take that light and run it through a prism and figure out what the line spectrum is of that light. So that would be like this unknown mixture. Let's say we collect light from a star, and we have this mixture of things, of wavelengths that the star has emitted. Now we want to know, what is that star? What elements make up that star? Well, we can compare the line spectrum of known elements to this star to kind of figure that out. So look at like lithium, for example. Lithium has this red wavelength here, and it looks like that wavelength is also in the unknown, right? But not just one wavelength from lithium has to be present. If lithium is present, then every wavelength from lithium should show up in the unknown. And look at this orange here. This orange from lithium does not show up in the unknown mixture. So because not all of lithium's lines show up, or wavelengths show up, we can conclude that lithium is not in our unknown. Now let's look at aluminum. Aluminum also has this bright red line here, but do all of aluminum's other wavelengths appear as well? So here's another wavelength that aluminum would give off, and that shows up in the unknown mixture. Here's another wavelength that aluminum gives off, and that one also appears in the unknown mixture. All of aluminum's wavelengths line up with our unknown mixture, so we can conclude that aluminum is in this mixture. This star, part of this star is aluminum, so it is emitting the line spectrum of aluminum among other line spectrums. But we can conclude that aluminum is part of what makes up this star. So that is hopefully something practical that you can kind of grab onto that comes out of all of these line spectrums and Bohr models. Now we're going to do something similar in our lab where we look at light and we try to figure out what that light is made out of. I'll also show you a couple Geissler tubes. So this behind me is a Geissler tube. It is a tube filled with argon gas. And again, as you run electricity through this, that electricity is absorbed by the electrons. The electrons for argon move up energy levels when they absorb that, and then they fall back down and they give that energy off as light. So we'll take a look at a couple more Geissler tubes. We'll try to identify some colors ourselves coming out of materials in our lab. And we'll work with this a little bit more. Hopefully you will work with it also on your end to wrap your brain around this concept. And then we can move on and talk about how this model shifts slightly to become our currently accepted model of the atom, the quantum mechanical model. Okay, so let me know if you have any questions. I'll see you in class.